stars cannot become black holes. We know this through the visible death of stars called supernova, and subsequently not turning into black holes but neutron stars instead, as well as the seemingly lack of an abundance of black holes in the observable universe when compared to how many stars we can see. So the next logical question is to identify the unique characteristics of stars that have become black holes or have the highest chance of becoming one in the future. Is it the size of the stars? Well, no, because Scuti is one of the biggest stars in the universe currently that we have observed, and astronomers and experts aren't concerned with Scuti becoming a black hole, even though it is 1,700 times bigger than our sun. Is it heat? Still no. Astronomers have proved that some of the hottest stars don't evolve in black holes. The answer is mass. The factor that dictates whether or not a star will turn into a black hole is mass. Although it isn't just mass on its own, it's the amount of mass in the space it inhabits. This is called the Schwarzschild radius. This radius is the border in which the particles and atoms in a mass experience an unstoppable gravitational collapse. For example, if we wanted Earth to become a black hole, it would have to be compressed into a ball with a diameter of less than 1.77 centimeters. Theoretically, a star in a binary system may be able to feed off the material of a partner star and achieve enough mass to undergo a supernova, which is often a precursor to black holes. Actually, binary systems are some of our best evidence when it comes to identifying the occurrence and positions of black holes. This is because due to the black hole's nature, there is no light in which to see it with, since it's pulled towards the singularity infinitely. In conjunction with another star, their orbits and behavior can be indicators of a black hole, as the immense gravitational pull of black holes affect the star's orbit majorly. HDE 226866 is a blue supergiant that was observed to have a strange orbit around which looked seemingly like nothing. And through investigations in 1964 by Charles Thomas Bolton, there seemed to be an immense X-ray source coming from the object the star was orbiting, and this led to the discovery of Cygnus X1, which was one of the first widely accepted evidences of a black hole. And what do we know about our sun, and how do we know this? Well, our sun is roughly 1.4 million kilometers in diameter, according to NASA, which may seem gargantuan to us mere humans, but in reality it is only categorized as a medium-sized star when compared to others that we know of. This conclusion was come to a series of trigonometric calculations similar to the processes used around 2,500 years ago by Greek philosopher Aristarchus, who figured out the diameter of the moon, and by utilizing the angle in which sunlight hit the Earth and that shadowing in which that light creates, an equation can be formed to predict the diameter of the sun. It is also believed that the surface of the sun is around 5,600 degrees Celsius, and this was figured out through employing and measuring spectroscopic data by satellites like the Parker Solar Probe. Also, the studying of the sun's wavelengths provides a pretty accurate estimate of the temperature, which is also signified by the color that it emits. And finally, we are fairly certain the mass of the sun is around 1.989 times 10 to the power of 30 kilograms. This value was devised through the rearrangement of Kepler's third law to this equation. All of these lead our sun to be classified as a G2V star, with G representing the temperature and the V representing that it is a main sequence star. The main thing we need to check is, does the sun have enough mass to turn into a black hole according to the Schwarzschild radius? Through doing the equations, we can see that for the sun to currently become a black hole, it would have to be 2.954 kilometers across. Which it is not, but that's understandable, because the sun is not a black hole currently, and we know that. Because of like the sun being there. In a measly 5 billion years, the sun is expected to run out of hydrogen to burn in the core and transition to a stage where, instead of in the core, hydrogen is burnt around the core. This sudden change in energy production will cause the sun to increase to a monstrous 200 times bigger in order to accommodate for the change. This expansion will unfortunately definitely spell the end of Mercury and Venus's life, as it swallows the planets into the unimaginably hot exterior. And it is even predicted in some models that Earth will also be swallowed in this enlargement. During this time, the core will eventually begin to burn helium as it enters a stage called the helium flash, which results in the shrinking of the star of around 2% of its total size. However, this won't last long, about 100 million years, give or take, as the sun will move into the phase called the asymptotic giant branch. Once the core runs out of helium, it burns it as fused to carbon and oxygen. This will cause another rapid expansion of the star to about the orbit of Mars. This phase will last for roughly 20 million more years, until the star reaches the point where it properly becomes unstable. Due to this instability, over a period of around 100,000 years, the sun will go through cycles where it loses a large amount of mass over a short period of time, and at the end of those cycles, large thermal pulses will explode out of the sun. As time passes, these thermal pulses will get more and more violent due to the effects of gravity, and thus make the sun so much brighter than it is now, an estimated 5 times brighter. These ejections will send so much space dust and gas into space that the sun will create what is known as a planetary nebula. The planetary nebulas are ejected space dust and gas that are so hot that they emit a subtle glow, but due to the sheer amount look like gorgeous glowing spectacles. Once this nebula fades away, all that will be left of our star will be a singular, small white dwarf, which will remain for trillions of years. The final theoretical stage of the sun's life will be becoming a black dwarf. Is when a star cools to the point where it is unable to burn any significant heat or emit any light. However, due to the white dwarf's lifespan being estimated to be longer than the age of the entire universe, none have ever been observed. Well, to understand how much time the sun is left, we need to know how old the sun is. Luminosity is a good measure on how old the sun is, as other stars we have viewed have displayed luminal characteristics closer to death or just after being born. The luminosity of our star is found through multiplying the surface area by the solar constant. This gives the sun a luminosity of 3.85 times 10 to the power of 26 watts, as well as the temperature, which can be derived from this equation. The rate of nuclear fusion by the sun is also important to determine how much time it is left. To find the rate of fusion, you need to find the mass defect between the hydrogen and helium when the excess turns into energy. This is done through subtracting the mass of 4 hydrogen atoms and 1 helium atom. Like this leads the mass defect to become 0.048 times 10 to the power of negative 27 kilograms. To turn mass into energy, we need to put it into E equals mc squared, becoming 4.3 times 10 to the power of negative 12 joules. Then you divide the total amount of watts the sun gives off by the joules given off in one fusion, which gives us the number of fusion reactions that happen every second of 9.3 times 10 to the power of 37 reactions per second. As in each fusion 4 hydrogen atoms are used, the sun fuses approximately 6.24 times 10 to the power of 11 kilograms per second. Then assuming the sun is around 2 times 10 to the power of 30 kilograms and dividing that by 6.24 times 10 to the power of 11 kilograms per second and multiplying that by 3.213 times 10 to the power of 18 seconds, you get around 10 to the power of 11 years. However, this number is not completely accurate, as these equations are acting as if the entire sun is hydrogen, which it is not, and as well as fusion only happening in the core. So only 70% of the sun is actually capable of fusion. This reduces the final number to just a bit lower, to around 7 to 8 billion years.